what happens if the interesting byte is second or the third one. I'm not going to do it now because I'll end up having like 30 minutes just explaining that. I'm going to complete the lecture, and I'm pretty sure I'll end up with like a 30-minute to spare. I'm going to do another example, okay? So let's continue the lecture and go back eventually to how do you do if the interesting byte is the second or the third byte, okay? I know this is dry, so bear with me. So I'm going to focus on eventually the network layer itself. We described things within the network layer, and we said each network layer will have a main properties or main criteria. One of them is forwarding information. Second one is defining the router algorithms. So looking at this internet network layer, mainly will consist of a forwarding table for the routing algorithms and the routing protocols, and eventually the IP protocol within the router to forward the packets. We define the forwarding table. I'll show you exactly how a forwarding table is happening. I'm going to show you now in a full details how will the header file contain what information and how will the information be interpreted by the table for the router to understand where to forward the information. Because last time I've done it, I just showed you like 110 and the interface will have number 1, you pass it through number 1. I want to show you today the full details of the IP address and how will the actual router know exactly when to forward the message. What procedure do they use? Is there a range of information? As I said, the table can contain large number of IP addresses. We want to focus exactly how can the IP address, or how the router will understand the range of IP addresses. I've already shown you that a network layer deals mainly with your data graphs. The data graphs are encapsulated by your frames within the data link layer, and then forwarded to as a physical to pass on to as a destination. And each device, i.e. whether that's your host or the router, will have the same procedure, dealing with the network layer and then passing on to as a destination. So all your actual interchangeable devices and routers deal with your 3 layers, and we explain why, because we're dealing with datagram and IP addresses, your network addresses, rather than only your switch. So within the data, you remember with your data link, we were dealing with switches and we only deal with 2 layers, and that's what's your physical and your data link. Meanwhile, we said with your network layer, your routers deal with the 3 main layers, physical, data link, and then with your network layers. Packets will be passed on from a host towards all the interchangeable routers towards your destination to arrive at your network. Yeah. So arrive eventually to the application. So the trick is from the network layer is to pass on that packets towards eventually your transport layer and then towards your application. So let's look at the diagram of the forwarding table. You remember I showed you that your forwarding table mainly will look at the header file inside the IP packets. So if I send a packet, how will the routing table inside that router work on the information? We showed, I think, beginning of the lecture, we showed something very important where if I send an IP packet will have a header file. The header file will contain the information where to forward the packet, to which line, to which destination eventually. So if I would have this router, and this router is connected to 3 outputs. Let's mark down 1, 2, 3, and then I'll have the third as a 4th one. We said that the information will contain here an indication to the router itself to look at the forwarding table and try to work out that range of information, where it should be sent. So usually I'll have that range, that information associated to an actual interface. So a 111 will be, for example, 2 and so on. That's an example. But in reality, what's inside this IP packet? What's the address? It's 32-bit rather than 3 numbers. So I'm telling you that your actual table should consist of a full range of IP addresses, and each IP address should have an interface. So do I have now, the question is, you have 64,000 IP addresses. Do you have each one of those IP addresses associated to an interface? Definitely not. So unless you have that big table that I cannot show you. of the full informations. Okay? So they said no, rather than doing that, we group them into set of users. We said that a range of number consists of from 0 to 100. Or if I want to go to those addresses, I go through route number 1. So we go through a numbers to reach a range of addresses. But in some cases, that cannot work because they need to have addresses itself. That depends on the subnet and how big is the subnet. So the subnet is not that big, which has 100 users. By all means, you can put them associated to a number of interfaces. But if they are about 60,000, 20,000, therefore you need to have them in a range. And each range, each group is associated with an interface to get to that address. Okay? So that's how actually router deals with IP addresses. So let's look at this example. The one I'm doing. Okay. So yes. So destination range of an IP address can be a set of number. It cannot match exactly the same. So you might have a range. The one can have like a 50 addresses going inside interface number 1. You have the other one like 60, the other one is 20. So there's no fixed rate of numbers inside each group because they are leading towards a destination. So I'm not saying that need to be divided eventually in the right number. It depends on your destinations exactly. Okay? So that's an example of a destination range. For example, link interface 0 is connected to that range of numbers, regardless of what are the numbers at the moment. And even any one of those did not match your actual IP. So let's say this actual header has an IP address would not match the three interfaces. We have something called otherwise. So if you cannot match to anything, there is a fourth link to send the information to. Okay? The interfaces are the links to your actual router. You remember when you said your PC has one interface because you have one connection to the internet, your internet service provider? Meanwhile, your router depends on number of ports you have. Depends on the interfaces. So a port and a router with 8 ports has 8 interfaces. Okay? So how do you forward? Again, I'm not routing. I'm forwarding the information inside one router. If you look at it, I'm forwarding information. That depends on your IP address range inside that routing table. Okay? So what if the number did not define or divided in a nice way, in the same range? We use something called the longest prefix matching. So what's that? Look at the table at the moment. The table has a number of range of addresses. So the first one ends with 0, 0, 0, 1, 0. There's no other information available. So that's the range of the information to go to interface 0. So what does that mean? If I would receive an actual IP information, okay, I'm receiving here a packet. The actual router will try to match the bytes bit by bit until he reaches a stage where we have a full matching. So for example, let's look at the first example. Look at this, the first one. Where is that being forwarded? Can anyone tell me? First example. That one. Where is that forwarded? To which interface and why? What are you doing? Tell me why. So look at this byte. 0, 0, 1, 0, 1, 1. Where is that? So that's 0, 0, 1, 0. So exactly if I match this until here, that's the first one. So what are you doing? The router matches what he has inside the header file with all the ranges that he has inside this table. Whenever he finds the longest match, he forwards it to that interface. Look at example number 2. Example number 2, he'll have a match until this stage. This will match exactly interface 1 and 2, which exactly you need to answer. Where do I forward it in the end? Do I forward it to interface number 1 and interface number 2? You tell me, where do you forward it? Continue matching. So if there is a continue matching, you take that long match until you reach the longest patch, then you forward it to that interface. That's how the router works. Guys, did you find any wallets here? Where did you go? So, if anyone finds something, you'll put it aside.
All right,
okay?
cheers. Thank you.
So, you come after, we finish at 4.
All right.
Come back.
Thank you.
No worries. Whoever finds we divide this, okay? So don't worry. You end up with 2 pounds at the end. Okay. Which interface we set? We have the longest prefix matching. So whenever you have the longest match, just send it to that interface. That's how the router operates. Is that clear? Any questions? Okay, so now we need to look at 2 main things. How will the router look like inside, what are inside the router, and how will the IP configuration, IP packet structure look like? Again, should be straightforward, theoretical information. So this is how the router will look like. Mainly the router will have what? The router will have an incoming link, that's your input port. You'll have the router itself, which has the actual processing units inside the router, and then you have the outgoing link. Let's create something here to show you the examples. So when I say incoming link, the input port, how does the input port look like? So that's your input port, that's your router, and that's your output port. So let's look at them in details. When I say input port, what's that? That's a link coming inside the router. What will that link be consisting of? Which layers? What are these? And not just network layer. What do you have inside? So if you have a physical link, what's that? Which layer is that? The physical link. That's the actual physical layer. That's the main word layer. Oh, what? The first one. The second layer. What's that? Data link layer. Exactly. So you have the input. The actual port will be consisting of 3 main layers: your physical, your data link, and finally you have your network layer. So that's your input. What's your output then? So because we started with those 2, what's your output? Same but reversed, exactly. So you have your network layer, your data link, and then you have your physical layer. Okay? And then inside you'll have the switching fabric of passing on the information. So how information is being passed towards those outgoing links to your ports. I'm going to look at them in details. So the 2 key router functions are 1, run routing algorithms or protocols, and we had an example of a DSR algorithm. Running that's inside your routing algorithm, inside your router. Second part, forwarding the datagrams. So we have routing and forwarding. Forwarding a datagram from an incoming to an outgoing link. So how is this happening inside the router? I'll show you in details. This is your switching fabric, which what happens exactly, how the information is passed on. Because you have multiple links coming in the ports and multiple links going outside the port. How will that operate? What are the procedure, the technique of passing on the information towards the ports? Okay? And finally, you have the router output, which is exactly the input, but in the reverse direction. Let's start with, and then you have inside the switching fabric, you have the routing processor. So this is the routing processor. That means this processor is involved of what? Of passing on the information towards what input and in which way. Okay? So you are passing on the information towards a port number, but what are the operations? What are the techniques? This processor unit inside that switching fabric is the person, is the actual responsibility of that object to pass on the information. Any questions? Let's start with the input. Very simple. We are defining what we defined in the first 3 parts of our layers. First layer, which is the line termination. Whenever I'm getting towards my actual router, I need to terminate that physical connection because I'm trying to deliver now a higher layer packets towards my inputs, towards my outputs. So the first part of it is the line termination, where your physical part will stop operating. Second part is your link layer. That's any type of link layer protocols, and we gave example of your Ethernet. So now the Ethernet is passing on the information towards your network layer. What happens in your network layer? If I'm sending so many information, you'll have a case of queuing. because you might have the incoming link is what? Much higher speed for the outgoing link. So you end up having number of packets being waiting in a queue in your network layer to be passed on to as a switching fabric. So the actual buffering will happen inside that network layer part of the input ports. Switching fabrics, how is that happening? We have 3 different types of switching fabrics. We start first one. So first of all, it's transferring the packets. The switching fabric, the main operation, is transferring the packets from an input buffer to the appropriate output buffer. So if I have an information being sent at the moment here on this packet, and I have 3 links, what is the operation inside that router to pass it on towards interface number 1? Or at least I have a switching fabric inside that controls passing on the information towards the right output, to pass it on towards the right interface. Okay? That happens in 3 ways. The first technique is called the memory technique, which is the oldest technique being used by the router, which depends heavily on the actual routing processor. So the routing processor will take the actual packets, find out using the operation of sending information to the processor. So the packet on will go from the input towards the processor inside, let's call it P, process the information, try to find the best way of passing it to which link inside that router. So what is this suffering from?
Delay.
Why? Because you need to send it to a processor will send it back and forward it to the right position. And you might end up with delay because there's in the output link, there is an actual queue of sending information. So that's the old one, and we're in the first part of trying to work out exactly where to pass information, the switching fabric of passing information. Serial bus. Can anyone tell me what's that? It should be similar to what we explained the serial bus in your beginning of the network layer. So just pass it one by one. Is there any process of forwarding? No. It just will do it arbitrarily. In a sense, passing on towards whoever is free, without involving the processor. But what will this suffer from? Why? Why go back and forth? No, it's waste, but not back and forth. If you have so many information trying to be sent, you can't send only one by one. So eventually, they will not be dropping, but you send one by one because it's been involved. So that link is being occupied by a packet need to pass towards an outgoing link. So you need to wait that packet to pass on towards exactly that interface for you to send other information. So you'll end up with waste, delay, depending on exactly what happens eventually. So that leaves us with the third part, and that's the crossbar over. We call it an interconnection one. And that's the more complicated and the most used at the moment with the routers. And if you look at the actual diagram of the crossbar, you can see exactly what's happening here. If you try to send an information towards one link and that link is occupied, it will take another path towards leading to one that's empty. So imagine you trying to pass on the information through this, and you start seeing some packets involved in here. You just pass it on towards another link, and then you pass it on towards you reach the right path towards the output. So you are going through different paths inside that switching fabric to reach the right interface eventually. That's a crossbar. So looking at this one, that's the most used one. There's no issues with it, unless there is a complicated, heavy usability in that routing, and that's out of the control of the routing itself. Okay? So ultimately, the crossbar will be the best technique used within that switching fabric. Any questions? Final part of the actual routing is the output. The output will be, again, you might suffer from a waiting delay because the processing time of forwarding the packet to its destination might suffer from the processing of information because there are information trying to be delivered on that link. So eventually that will suffer as a queuing buffer inside the output link. That will then pass on to its data link switch and therefore to its line to be passed on to its switch. The buffering required when diagrams arrive from fabric faster than the transmission rate. And the scheduling discipline choose among the queue datagram for transmission. That's straight. We explained the delays in full details with over 4 delays, so I don't need to go through them in full details again. Okay? Okay. With IP datagram. format of the IP version 4 datagram. So, what this consists of? Let's look at it. Mainly, version, what's that? How many versions of IP addresses do you have? 2, 6, and 4. So in here, you're defining in the beginning, this is an IP version 4. So everything else will depend on that version. If it's a 6, then even the structure will look different, but the router will know exactly how to deal with it. So that's the first operating part within your routers to know how to deal with the packets. I'll look at some of the information. I'm not going to give you the full information because it's just waste time. Type of service. I want someone to give me what exactly is type of service. I'm dealing with an IP datagram. When I say service, as a user, what are the kind of services you're looking at? What's that?
A request?
That's not a service. That's a request. But when I say service, so that's for if I mean quality service. What would that be associated to?
Reliable or reliable.
Exactly. So if you want a reliable service, so you need to define in the beginning, I want an IP reliable. So in other words, you are telling the IP packet to deliver to the TCP because you want a reliable operation. For example, you want to have extra qualities, you want to have speed. So you're indicating the type of services you require within this IP packet. Because this IP packet is optional, you can't have anything inside. That's how strong is this IP packet, and that's why it's still used at the moment. Everything can be optionally changed inside the IP packet. Again, you cannot remove those. You remember that I said there's an overhead? Because even if I choose some services, I cannot take rid of the length, the option, the data. There are some things I cannot control because they are in the structure of the actual packet. Okay. Let's explain what this 16-bit identifier flags fragment offsets. I'll ask you a question. If I'm trying to pass on information from a datagram and encapsulate it eventually using a segment, so I'm passing on from network layer 3 towards your data link in the second layer. So what do? I encapsulate this at the header of the actual datagram and send it. The question is there a limit in size? If I'm passing a datagram towards an actual frame in a data link, is there a limit? Can I send as much information as I can? Or is there a limit depending on your protocol in the link layer, the data link layer? What do you think? Must be a limit, isn't it? So if I leave it open, that means I can send like 200 meg in one packet. Can I do that? Definitely not. Neither then the network will accept that. Then the packet will carry that information. There is a limit. Who decides that limit? Therefore, there is a limit associated with the next layer, with your Ethernet, with the cable, with the actual connection. This will enable you to control exactly the size of the packet. So what happens if I'm sending 100 bytes? What do I do? So if it's bigger than the allowed, so you're allowed to send only 50. What do you do with this? You fragmented the actual IP. So you start splitting your actual packets into smaller packets. Who controls those information? So how can I deliver those in the right order? How do I know they belong to the same packet? And how do I know it's going to be the last packet of that part of the actual phone size? Those three identifiers will be the ones to identify that. In the next slide, I'm going to explain this in full details, but I just want to show you those are the three that requires to deliver each part to the right destination and how is that done, okay? By the way, IP version 6, don't divide the actual fragments. It will use one size and it will enable the Ethernet to use it within the allowance, so it will know exactly the allowance of that Ethernet and send the size with that allowance. So if it's 500, it will divide every IP version 6 packet into 500. Okay? Don't worry about IP version 6, let's focus on 4. it's complicated as it is. Time to live. I love that. What's that?
How long before it gives up?
Sorry, what's that?
How long before it gives up?
What does that mean? What does that? So we use timeout. I'm going to turn to you. We use timeout with the table entries, and we said if I create an entry in a table, it will have a time of 60 minutes. If that table, or that IP, if that switch, if that actual physical address is not being used, this will dies out, and eventually no one will use it. In routing packets, why do I need a timer there? Why do I need time to make this? That's exactly. In some cases, you have that packet, that division, just got lost. Put it that way. And it starts going inside that actual network all around the place, just creating overhead. So if I would have number of hops saying that I'm allowing this packet to go 20 times between number of switches, and every hop it will come goes in lower to a number until it reaches 0 and did not reach the destination, it will just die. Wow, that's it. It just dropped. That's the right word. Is that clear? Well, because I'm saying live and die, that's why. So, is that clear what time to live is? Good. What else? Upper layer. Someone. What's upper layer is? Why do I need that? Why do I need the upper layer? Someone. If I'm sending information from the source to as a destination, this goes back from here, data link network, then to as your upper layers. So why do you need that? Which layer which exactly protocol inside that layer you want to deliver information to? So you want to deliver to the UDP with no reliable service, or the TCP because I need reliability. So choosing the actual protocol is an option again. It's not like an obligation you want to choose it, but depends on your services to use exactly which one of those. What else? What is your source and destination? That's your source and destination. If I go back to your ARP, remember that IP source and IP destination? That's it. Here are the information required. What else? What is your header checksum? What's that? That's it. For example, can be anything. CRC, your error detection method. Okay? So that's here where you have your error detection. Data. That will have the data inside. This is the actual and the most important information. This is the actual data coming in from your lower layers or the higher layers. Any questions? Final slide. IP fragmentation. So let's read the slides. As I said, the network links have something called MTU, which is maximum transfer size. I think it should be maximum transfer units. Okay? So there's a size allowed to send those frames into those actual, from a datagram to a frame. So each datagram should be divided to the right amount of size to pass on to as an information to as a destination. So why is that? You have different links and you have different MTUs. So you might have a link, a fiber optic, allow 100 bytes. You might have a twisted pair, we allow 200. So these are different sizes. So these numbers, the MTU value, which will indicate to the IP datagram to actually divide the actual size within the boundaries. You cannot go over the size, therefore you need to do IP fragmentation. Is that clear? How is that working? How do you control that? Just explaining the next slide. Yeah. So large IP datagram is divided and fragmented within the network. One datagram becomes several datagrams. Remember when we said when the encapsulation is not simple as one packet being passed on? We said we divide that into multiple and each one of them is encapsulated? That's what happens. Fragmentation of the actual messages. Then it will be resembled eventually in the final destination. So that's the final part when you need to send the information to as the host you want to send it to. In that place, you will have the resemble again. If a header bit is used to identify order of the related fragments, again, how do I know that each one of them belongs to the same identified packet? How do I know it's the first, the last, the middle? How do I control the sequence of those? And eventually, how do you know this is the last part of those fragmented packets? We need those three, as we explained this in those three parts, 16-bit identifier, you need the flags, and then you need the fragment offsets. What are these? I'm explaining to this class. Let's look at an example. Assume you have 4,000 byte datagram, and your MTU is 1,500. So how many this will be divided into? This will be divided into three parts. That's your maximum size unit. So that's what you allow you to do. So again, what exactly you need to identify exactly the size of the fragments. Now I'm sending 4,000 bytes. If I divide that, depending on my MCU, how many do I need? Just do a math. Divide by that 3. Is it 3? Is it 2? So if I have 4,000 divided by 1,500, should be 3, is it? So that's 3 fragmented data groups. Each one of them will have the length, i.e. the size, has the ID, flag, and finally the offset. What is your ID? Can anyone tell me what's an ID?
Sequence of packets.
No, it's from the name. So if I would say I'm dividing, let's make this more interesting. I'm dividing those 2 packets, this one and that one. Let's put a different color. So these are divided into small parts. Yes?
Identify them all together. They're all of the same original package.
Exactly. So if I would have this black one and that's the blue one, I need to have some ID to them to know that those small sizes belong to the same fragmented datagram. So the ID identifies exactly where is that packet belongs to whom. That's it. That's the ID. So if I give it an ID, for example, 700, and this one is 500. Every ID with the number 500 belongs to B, and every ID of 700 belongs to A. That's it. That's identifying that exact part to whom it belongs. So what is your offset? What do you think? Yeah?
Is that how far away is from the first packet to send?
So,
Start.
yeah, okay, good. It looks fine, but what is it control? So if I would have 4, I have 3 parts. I have 3 fragmented datagrams. What is the offset? So what's 0, what's 185, what's 370?
Data.
What's that?
Data.
So again, what are you identifying here? What are you controlling here? So these are delivered in this way. Look at this. What are these? How do you resemble them in the right way? You need to have exactly the order of them. So this numbers identify the order of those fragmented datagrams. So what are these numbers? That's reflected to the size of those. So don't worry about the numbers. The sequence of the numbers should identify which one is the first, which one is the last. Final one, what is your offset? What is your flag? Sorry to confuse myself. Exactly, that's it. Just identifying the last one. Because if I'm sending like 4 or 5, the receiver would not know exactly how many are they. Even if they are in sequence, you need to know, I'm stopping now this ID of 700. I've collected them all, I'm forwarding it to it, I've already analyzed it, forwarded it past to the higher layers, whatever. So these are your 3 identifiers. Any questions? Is it clear?
What's flag like?
Sorry?
What's flag?
Just beats should be fine. Okay, guys, I'm finished. No, wait 1 second. Okay, wait. I'm not finished. No, just 1 second. The offset is just identifying the order of the messages. I shouldn't say it's finished.
So can it be random numbers?
Yeah, no, it should be in sequence, but the size of it depends on the size of the packet. Okay? So guys, when I said finish, I mean finish. Oh, let me use that. Guys, when I said finish, I mean I don't have any new material. So what I'm going to do now, I'm going to give you, no, I'm not giving you too much. I'm going to give you an example, a final example. Oh, okay. That's for your own good, it's not for me. I'm going to give you a final example as an interesting byte being the second or the third. Okay? That's it. Just one example. It will take 10 minutes, okay? So, okay, but guys, if you want me to do, I'll leave it to you. For those who want to stay, by all means. If you want to stay, by all means. If you want to leave, just do it fast. 5 minutes, okay? Okay, I still have 20 minutes. I'm going to give you an example, and I'm going to do it again. It was part of the last year exam, so it's your fault. Impossible to leave, is it? Okay, guys, I'm going to give you a small example, and just stop in the middle. I'm not going to do the full table. I just want to show you something right now. What you just told me about it, the 255 thing. That's a small thing, okay? So. Okay, so let's focus on this example. Look, let's take this example, 10, 0, 0, 0. And I'll have this, let's make it 60. No, that's 16 will be example 18. Because that would end up with class B. So 18. You tell me, what is 18 now?
One.
The mask, exactly. That's how the number of ones inside your mask. And these are 8 ones plus 8 plus 8. So that's 8. 16 plus 1, 2. How many zeros in that byte? So that's 6 zeros. How much? Have I finished?
No.
Yes.
I still have 1 byte left. What's that?
8 zeros.
8 zeros, exactly. Thank you. Question is, where is your network? Where is the host? Network, all ones. Network,
Integer.
that's the ID. What's that? Pure host. So, okay, what does that mean? Is there anything new here? This is the same analogy. I'm going to focus first on my interesting bytes. Well, not only on the interesting bytes. I need to know the subnets. Subnet is number of ones, 2 to the power of ones, inside my interesting bytes. That's 2 to the power of, that's 4 bytes. 4 bytes, 4 subnets. Even I'm ones. That's 4 subnets. Okay? Perfect. How many hosts do I have? What's the formula?
2 to the power of 0.
2 to the power of zeros minus 2. What's the value? So 2 to the power of what?
6.
2 to the power of 6?
Yeah.
What about those zeros? Are they not hosts? So now the trick part is 2 to the power of
6.
14. Again, 6.
Are we not just dealing with
No, that's
one host?
the formula says 2 to the power of ones inside the interesting bytes. This is 2 to the power of zeros. Minus 2.
So why are we
Okay?
not using the ones on network layer as well? On subnet?
That's how it works. You are working the subnets based on your IP address, the actual interesting bytes, but you work your hosts on the full zeros of the actual device. Is that clear? Why? Because now the range of the table will be different. It will not stop on 32 and 31 on the increment. It will go to 255. Let's continue. So, what's the value? That's 2 to the power of, what's the value? So that's 8 plus 6, so that's 14. Minus 2. Don't give me the one, I'm not worried about that. Okay? But you need to know that now the range are different with the actual hosts. Tell me now exactly what's your increment? That's 2, 5, 6 minus 128 plus 64. What's the value? Okay. What is it? What's the increment? So end up with?
192. Oh, sorry.
So that's 256 minus 192, I'll give you 64. So your increment is, because you have how many subnets? 4. So now you need a 64, is it? So let's work out the table. That's the tricky part we would be interested in. Worked out. Again, I'm going to do this again in the tutorial, but I just wanted to give you a heads up. When you do work it out, you will understand what's happening at least. So, I'm looking for your subnets, your increment, first, last user, and the broadcasts. That's your table. That's the subnet. That's your first address. Last, and finally your broadcast. So what's your first? Give me a subnet. Let's start with the subnets. We have 4 subnets. I'm going to do 3 of those. Okay, I'm going to do 2. So what's your address? That's subnets. That's 0, 1, 0, 0, 0, 0. That's your first subnet. What's your second subnet? Incremented by what? 64. So what's the second subnet? Be careful. Where is your interested byte? And increment that. That's 10 plus. So that's 0. 64, 0. Your third subnet. 10, 0, 128, 0. So I'll stop here. Tell me the broadcast address. Yeah, did I do everything? Oh,
So why would you
because your increment is. No. It's 256 minus 128 plus 64. And that's 256 minus 192. That's 64. That's your increment. This is how you do your increment. Okay? Is that clear? What's your first address? Give me the broadcast first. Hold on, let's start with it first. What's your first address, guys?
10.0.
Okay, 10.0. Point. Perfect. What's your broadcast address? Sorry? So that's 10. Broadcast.
0, 60.
Wait. 10.0.63. Oh, you go. So no. No, you don't. So what's here? Why? Now you go to the range of the full range of the actual IP addressing. What's your range of the IP address? It goes from 0 to 255. In the last example we had, the interesting byte was bounding us towards only increment inside that byte. In here now, I'm incrementing only this byte, but these are hosts. Okay? So they go to 255, not stopping there. So what's your last address in here then? That's 10, 0, 60,
2.
60. No, say 63. I'll tell you why. 254. If I say 62, what happens to 63, 1, 63, 2, 63? You just wasted a full range of addresses. When you said 62, you skip 63, 1, 63, 2, 63, 3. You just skip that.
Yeah.
So be careful. That's just an increment. Is that clear? Let's do the second one. Tell me your first address.
6.4.
Exactly. 641. What's your first address? What's your broadcast one? 10, 0, 127, 255. Last address? 10, 0, 60, 127, 254.
Do we for that last one?
You have 2 left because there are 4 subnets. But did you understand that person? I'm going to do this again in the tutorial, but we're finished, okay? See you in the tutorial.